I think we do have one large homework assignment and then computer assignment, and then just the term project presentation, which I would hope that we organize all the oral presentation during the last week of this course. But of course, that would be very tight. If any team or individual would like to present in 1 week before the final week, then I would hope that I can host that. Okay, so tonight we are going to talk a little bit about some specific optimization technique which take the advantage of the convexity of the. For instance, you know that for nonlinear optimization problem, if you don't know any specific structure of the problem, it's usually very difficult. So now we can see that in general, if the original problem is not linear program, if you can convert that into a linear program, it will be very nice, right? And sometimes maybe you introduce new variables or introduce new constraints. But when you can convert that into linear program, then nonlinear program usually is harder to solve, especially when you develop some efficient numerical algorithm. You can always try to convert the problem. However, sometimes it's not feasible. But then we try to look into some problem. For instance, originally it may not be a convex program, but we try to convert that into a convex program. So I will make an introduction to some specific type of this problem, some specific type problem that's doable, which is called the geometric programming. And of course, some theoretical background, which if you are not very familiar with the term, then I will try to explain to my best extent. And then also I will try to focus on some examples and how that can be applied to some interesting engineering applications. Okay, so here's the background, and that's something I don't think it's necessary to first talk about these terms, but I would say if you have some function f, which this is some mapping because we have this f of x contains n-dimensional decision variables, x1 through xn, and then that map into some real line. That's the objective function, for instance. And this objective function, if you look at the decision variable, it contains x1, x2 through xn, but then it raised to the power of a1, a2 through an. And that's like what? The product of these decision variables, right? Raised to some power. And this a1 through an are just some constants. And this has a name. People call that monomial function. And then, for instance, if you have a collection of these so-called monomial functions, then this function, if you have k terms of monomial function, you take the sum of this. That's called a polynomial function. I mean, the name doesn't really matter, but the point is that this, is it a convex function? No, it is not, right? Yeah, it is not a convex function. And if you try to optimize with respect to this type of function, usually it's hard. You say it has to be some nonlinear optimization algorithm that can solve this. And also, in general, you can only hope for finding a local minimum instead of a global minimum. However, if the function has some convexity, then that's nice, right? So we're going to talk about, for instance, by just doing some transform, it's possible to solve such a problem. And think about geometric program is to handle some monomial functions or polynomial functions. And what we can do is, for instance, if the objective function is a polynomial function, that means it's like the sum of this product of the decision variables. And then your inequality constraints can be what? Also polynomial function, but your equality constraints have to be monomial functions. And then, of course, your domain in general is like all the real, in the whole real space, or maybe the positive of real space. And then this type of problem can be converted into basically convex program. And how? In fact, if you think about, like, this is like the product of the decision variable, right? However, we cannot handle the product. So what do we do? Take the log, very good. So take the log, it will become what? The sum of these decision variables, right? And then that has nice structure, right? Because the way this problem appears to be nice is because after taking logarithm on the objective function, things become easier. And then another relevant question is when we do optimization problem, taking log wouldn't really change what? The optimal solution, right? Meaning what? If you have some kind of a monotone function like a log, then what? Then in general, if you have like a minimum point, after taking log, you won't change that, right? That's why, for instance, you want to maximize the log likelihood function. You could also maximize the log of the likelihood function, right? So in this case, we can change this non-convex program to a convex program. And the reason is that look at the left-hand side, you have this objective function which contains k0 terms of this polynomial objective function. And then you have polynomial inequality constraints, and you have this monomial equality constraints. And then what? Rearrange this by somehow by some exponential function where you have this sum and the exponential function. Now you try to do a change of variable, saying that this new decision variable, you say xi equals to e to the power of yi, and then also make this constants c to be e to the bi, and this b can be determined by just take the natural logarithm. And doing this new, after doing this change of variable, you'll have what? Sum of e to some linear objective function, right? You'll have the sum of a bunch of exponential functions. And this exponential function contains what? Like a fine transform of your decision variable y. Okay? Is that clear? Because this is the product between your decision variables, right? And then now, if I change this decision variables to e to the power of y, right? Then this is like e to this thing becomes linear. Like what you just suggested, taking log of this will give you just a linear function of decision variable y. The product of decision variable x1 through xn will actually give you what? E to the power of a linear combination of decision variable y1 through yn. And this is an essential transform to make the problem become a convex program. So that's why this is called a geometric program. Once you convert this into a new problem where the decision variable becomes this y, then this actually is a convex program. Can you see that? Well, it's not very obvious, but think in different stages. For each term, is it a convex function? Is this, for instance, if you only look at this term like A transpose Y plus B, is it a convex function of Y? It's an affine function, so of course it is, right? And the E to the power of that, is it a convex function? I need to think a little bit. E to the power of A transpose Y plus B, for instance. That means is essentially you need to know like this E to the power of X, is it a convex? Okay. Okay, so now I hope that you are convinced that this exponential function is a convex. Okay, convex function. And then a linear combination of convex function, is it still convex? Yes, okay, so basically we want to make sure this is a convex objective function. And then also the constraints are the convex set. Okay, that means basically we need to verify that. For inequality constraints, because it's basically the intersection of this exponential, so it's convex. It's not convex how, but it's essentially the like the pseudo-convex subset. The only problem is this term, right? This can only be what? A fan function, meaning that it can only be straight line in this hyperplane, so that when you intersect some kind of a polyhedron or in general convex set, then this hyperplane intersect with a convex set still is convex. So of course, after such a long argument, we see this is a convex program. That's the key. So what I'm saying is, in general, geometric program can be converted into convex program. Okay, so now you can see that this actually can have different extensions. For instance, this is one way to extend this geometric program to some other settings where you have f of x, which is a polynomial, and h of x is some non-zero monomial function. Remember, monomial function just product of decision variables raised to a certain power. And polynomial is just a linear combination of these monomial functions. And then, for instance, if you say, well, f of x is less than or equal to h of x, means what? F over h is less than or equal to 1. And these are very interesting properties. Like f of x is less than or equal to a, means this can be normalized. And if this properties you understand, and also for monomial function, in fact, doing just 1 over a monomial function, you can change the maximization problem to minimization problem if you want to, by just do an inverse. Meaning that basically by just changing the coefficient of your product in the raised power, a maximum and minimum problem in the monomial function can be converted. Okay, so these are possible ways you can manipulate so that some, yes?
Sorry, Doc.
Yeah.
Monomial function.
Yeah.
If you multiply by -1, does that also work?
If you...
Is maximizing a monomial function same thing as minimizing?
Yeah, of course. For any function, you can do that.
Oh, okay. So this is an additional property.
Yeah, this is additional property that's applicable to only to this type of problem. And for this type of problem, what is interesting is that you can actually do some functional substitute to make the problem look nicer. For instance, here you have this f of x, q of x, and h of x, all polynomial functions. And then you say, I want to minimize this y of x, which is f of x plus some q of x raised to the power of a and h of x. Now you think this is hard, right? Because I need to handle the product of polynomials. In general, geometric programming objective function is only what? Only the sum of monomial functions. And then you have product of polynomial functions. How can you do that? Well, that, for instance, you try to make some change in this by introducing a polynomial constraint. Then you have decision variables, and then you have a new decision variable and a constraint. Then you make it a geometric program. Does that make sense? Well, this t is a new decision variable. You need to optimize now, because now you introduce y of x equals to f of x plus t to the power of a, h of x. And your decision variable include what? Both x and t. And also you have a new constraint on this. While t to minus 1, q of x is less than or equal to 1. I remember this is a product, which means if originally q is a polynomial, then this is still a polynomial function, right? That means you have this as a standard geometric program. Well, q is just a polynomial function. Well, that's a constraint to convert original problem into a geometric program. Original optimization problem, the objective function contains what? The product of polynomials. And there's no direct way you can solve that, right? It's not a geometric program.
So you assume that, you can find a lead.
Yeah, so this is straightforward to say that I just add a new decision variable that I call t, right? And then this t multiply this h of x. This is polynomial function. But then this t, because I replace q of x by t, then I need to add a new constraint, saying that t is greater than or equal to q of x.
T is now not a function of x. It is now independent.
It's just a new decision variable. Yeah, you need to optimize.
But for that, you have to assume that t is bounded function. So how do you find a t which is t is greater than or equal to qx for every x?
Well, not for every x, but you need to satisfy this constraint when you do the optimization. Meaning that when you solve for decision variables x and t, you want to make sure that t is greater than or equal to q of x.
Yeah,
Okay?
you assume the existence of, like, you know,
Well, if original optimization problem has a solution, then, yeah, of course, after doing this, you will find out that your optimal solution will be identical to the original one. And the assumptions made in the original polynomial functions will make sure that whether you can find the optimal solution or not. I mean, like what you said, maybe unbounded set, then guarantee you can have a global optimal solution. But that's not really crucial when you do a transform, because the original feasible set will not change. But you do introduce a new decision variable and a new constraint. And we did that even for a problem which originally is not a linear program. We changed that to linear program, right? I think in maybe first lecture, probably nobody recall that. And now we have a better way to just video recording whatever lecture notes available. Then you can really look into the archives and find out. Okay, so this is one extension. There's another example. You can see that original problem, you can see now involved with decision variable x1 and x2. And what? This looks like what? A polynomial, another polynomial function, right? So it's like the product of polynomial function we can now really solve. And that's just illustration. By solving this, you need to invoke nonlinear optimization technique. And you can only hope for finding a local minimal. However, if you introduce decision variable x3 and x4, then you can say this whole thing is x3 and this whole thing is x4. But then you need to introduce something like this, t1 and t2, to ensure that this is satisfied. And then by doing some manipulation, you'll see now my objective function is actually a monomial function. And then my constraints are all polynomial functions, right? So this original problem can be converted to a geometric program by introducing new decision variables and new constraints. The price you paid is that you formulate the problem from unconstrained optimization to a constrained optimization. And also you have new decision variables. And the nice thing you can claim by doing this transform is that what? You can use a convex program package like CVX or whatever software to find the global minimum instead of settle with a local minimum. Okay, so with this type of setup, then what you see is that you can have generalized extension of the problem by looking at original problem contains what? F of x, which is a polynomial function, and q of x, another polynomial function, and then h of x is polynomial. But then u of x is monomial, And then you have this kind of strange term, q of x over u of x minus h of x raised to the power of a for some positive a. You say, well, no way, this can be geometric program. Well, originally this cannot be, but remember, this thing bothers you, right? And in general, we do what? Like substitution, just introduce a new decision variable, put constraint on that. And hopefully, that can convert the problem into geometric program. And by the same token, you introduce this z less than or equal to u of x minus h of x. Then you have objective function y x and z equals to f of x plus q of x over z to power of a. And now this q over z to power of a is a what? Polynomial function. So overall, this is still a polynomial function, right? And then you constrain, you can show that it is also polynomial because by this assumption, u of x is a monomial function. And then what? Polynomial function over a monomial function is still polynomial.
I have a question. For example, when you make this kind of transformation by introducing new variables,
Yeah.
the solution of these transform problems, whether it gives the solution of the original problem?
Yes. Well, under some regularity assumptions, I have to make it a little bit rigorous. But still, if you think about it, if your original problem has an optimal solution, this basically is equivalent to solving the same optimization problem, but by just changing variable. And they have the identical optimal solution. But of course, the optimal with respect to the new decision variable z, you don't care. You only care about x, because that solves the original problem. And this problem, of course, require you to add new constraints and new decision variables. But still, it's better because you invoke a convex program package. Similarly, for instance, if you have 10 decision variables for nonlinear optimization, now you change it to 20 decision variables for linear program. Do you want to do that? I would always recommend you convert the problem to linear program, especially when the problem size become an issue. Okay, so for this, of course, I can keep doing. Just give you some idea. In general, there are some non-convex optimization problem you can actually change that to geometric program so that it will be convex program. In this example, you can see it's just some specific way to make this term go away, because this denominator has something that makes this not a polynomial function. So we introduce this z so that we have a polynomial function, we have a polynomial constraint. Original problem becomes geometric program. Okay, so now you see there are different ways to make this transform. Okay, and then of course, if you are mathematically prone toward what will be the general conditions to make such a transform, in general, that's hard to answer, but at least you'll see some typical patterns. And sometimes you may say, even if those things that don't work, still you can do appropriate substitutions and transformations to give approximate solution to certain non-polynomial terms. Meaning that if the function is a sum of polynomial and some non-polynomial terms, then you can approximate those non-polynomial terms by some monomial function and then apply geometric programming technique, at least to find a close to optimal solution. And that's still a good idea. And also, if you have some logarithm term, you can make sure that the limiting approximations will actually allow you to transform logarithm term to geometric program structure. And if you have exponential terms, in general, it can also be approximated. And most of the time, I think it's just a way to do Taylor series expansion with appropriate number of terms would be good enough to do the expansion. So overall, I would say geometric programming is actually a very powerful optimization technique, especially in recent years. many engineering design and also even in mathematics, like doing operations research, people cannot ignore the abundance of the applications where the optimization problem is formulated as geometric program. Okay, so there are many engineering problems which can be studied using geometric program. And most of the design systems in general can also be decomposed so that it contains different blocks. And also sometimes we can use different techniques combined together to solve a more complicated problem into small manageable sub-problems. And this includes many different types of examples. Like in mechanical engineering, there are optimization problems like how to use the C-power, how the gas transmission and compressor design can be tailored towards some design parameters, and transportation problem for the shape operation and design. And in electrical engineering, there are different designs related to how the transformer should be operated, and electronic magnetic device can be optimized in order to achieve certain performance metric. And also in chemical engineering, there are some problems where optimization of distillation and some other processes are important. So there are different engineering applications that can be cast into geometric program. Also, another type of problem, which in general is not really a geometric program, but can be studied based on the same token. For instance, this so-called Frobenius norm diagonal scaling is one very useful technique that you can study to change the problem structure so that the optimization problem can be handled using efficient numerical algorithms. Well, the idea is that, for instance, you want to create some n by n matrix M so that you can scale your decision vector U by y equals to I multiply U, so that this y, the new function with respect to y, has a better, how should I say, has a better range or better scaling law for your decision. And that sometimes can create numerically stable routine rather than unscaled problems. Okay, so should I proceed with some examples, or you want to maybe get into some numerical examples, simple numerical examples, just to get familiar with geometric program? Okay, so okay, so we look into some example where actually these examples are found in another textbook that's Introduction to Operations Research, which actually adopt some real-world problem and try to at least give you some hands-on experience about like how those field engineers solve the optimization problem routinely, and they use some very effective commercial software or maybe educational software for study this type of problem. And this is one application that's called the multiple stage distillation for some chemical plant. And the most common way to extract fresh water from the ocean is called the distillation. And that means you vaporize fresh water from the seawater. And this technique is very expensive. So if you want to reduce the cost of distillation, excessive heat in the vaporized water is often used to vaporize more fresh water from seawater. And the procedure is called multiple stage distillation. Well, that's just the background. And then why talk about that? Because this can be studied as an optimization problem. Okay, and here's illustration of the multiple stage distillation process. And here there are different stages where you see this is stages that seawater coming in, and then you put some input heat, and then you heat seawater to vaporize the next stage and vaporize next stage. And then here you have fresh water, seawater coming out, so that basically the first stage is exploited by the next stage, by the second stage, and so on and so forth. So that basically after the whole procedure, you get the distillation product. Okay, so now we need to study like how many stages do we need and how to design these stages, like how to put appropriate amount of water and the heat. Okay, so here there are some parameters used in this problem. Let's call this delta T the temperature drop on every distillation stage. And this delta T is the temperature difference between the first and the last stage. So that's like the total temperature gradient you see. And then this H of V is the heat of the is the heat for vaporizing 1 unit water. And small h is a heat transfer is some kind of heat transfer coefficient at every distillation stage. And A is the plate area at every stage. Q is the velocity of the fresh water vaporized at each stage. And Ca cost for the plate per unit area, and then Ch cost per unit heat. So now you see defining this, then you can do what? Write down objective function and then write down the constraints. Okay, so now of course everything boils down to write down all this heating procedure as a physical process to what? The cost you are going to spend for the distillation. Okay, so now here's the objective function where we need to still specify different terms. I'm not sure if I can do this. Multi-stage. Okay, so from here probably I can go. Okay, so now this is optimization problem. The objective is to minimize the cost for maybe one distillation stage. We call this G0, where you have what? The capital cost and the operational cost. And the operating cost depends on what? Well, you have cost per plate per unit area, and then you have the cost per unit heat, right? And then the velocity of the fresh water to vaporize in each stage. Okay, so basically, now you see this is like the product of this, and this is also the product of a bunch of other things. And you have some factor called the capital recovery factor, which is used to calculate the rate of amortization, which in general is the amount on the amount per unit time over initial capital cost, so that you have some cost model, which is what? Actually the product of a bunch of decision variables. So now you see what? Some sense of geometric programming type of problem coming out, right? Okay, so now these are variables actually connecting what you can do in each stage. Okay, so questions? Well, then later, of course, once you have the constraints, then you can solve. But then I don't, because, for instance, if you have the operations research textbook, it's like maybe 3 to 5 pages detailing how to solve that by putting variables, putting numbers, and run software and solve it. So this is basically some problem. You can see that you have some, like the product of the decision variable. And maybe later I will try to have one application that contains all these thinking process, how to really solve geometric program. And there are several possible applications of geometric programming also in shipbuilding and also that's also where the early literature talking about how to use geometric programming as an operations research tool to minimize the cost for shape operation. And if you look at this, you will say, wow, that's even harder than the first example. Because even to remember what are the decision variables and what are the things you need to find from the field test is hard. These are variables and parameters for the model. And you can see for different colors, I hope that at least illustrates something like the number of ships, dead weight capacity in tons, and utilization factor, and service speed in knots. And these are things like a discounted building cost of ship, exclusive machinery per ton weight, and capitalized fuel cost per ton. And some are parameters that you study, and some are decision variables you need to optimize for ship operation. Like ships loading displacement, these things usually you can or you cannot optimize. You can, you cannot. Like number of years for discounting and capitalizing, and total number of operating hours per year. These things, okay, more or less you cannot really optimize, right? And for instance, service speed, that you can, right? For instance, you can design like how the ship should be typically operated. So these are variables and parameters that you can optimize. Other things are those that you cannot. And of course, you can say, what will be the objective function? Well, minimize discounted ship cost plus discounted machinery cost plus fuel cost. And sometimes, originally, you may say how to write that down. Well, in general, I would say even if you ask a field engineer, probably it's hard. You can only have a very general guideline. And then sometimes you may say, I know geometric programming, so what? So I will try to at least make it look in such a geometric form. And that's why, for instance, this so-called Admiralty formula was introduced in the original paper published in the 1970s. They say, well, I want my objective function to contain this form, okay? And the fuel cost contains like the total time using the fuel, and also the fuel using rate. And also you need to consider different type of constraints. Like there must be enough ships and voyage to meet the required tonnage per year. And the utilization factor should be bounded by the maximum possible value. Some additional constraints could be put so that the optimal number of ships must be integer. But in practice, for instance, people say, well, integrality constraint is not so crucial if you talk about many different ships. You say, well, many different ships, then the total number is large, then a simple round-off solution is probably valid. So now you see engineering trick. If you make integer constraint there, then you know the problem is hard, right? Integer programming is in general an NP-complete type of problem. However, they say, well, I don't want to solve that problem. I just relax the integer constraint and later solve the solution and then round it off. Is that good? Most of the time it may not be good, but I think in this type of application, they can justify it's good enough. Okay, so now what we see is that the formulation of the optimization problem after substituting the parameters by proper values from those authors who study this kind of shape operation, which I don't know why they chose those numbers, but of course, if you want to do some engineering optimization, you need to study that. And then objective function is this, and constraint is this. Now what? You can see this is what? A polynomial function. This is what? Another polynomial function, another polynomial function. So you have standard geometric program. And then, of course, the authors just say, well, for this type of, they call small scale optimization problem, because in fact, even though there are many decision variables, but still you can run convex program routine, you can solve the optimal solution. But why you believe this is the optimal solution? Why? You don't? Okay. Is there any particular reason you don't? I think because there's so many decision variables, you don't trust the MATLAB program for optimizing this. Well, compared with the real engineering optimization problem, this is already simplified. I would say if you do like a F-min-con type of optimization, I wouldn't trust you find the global optimal. But after converting this into convex program, in fact, you should trust that the existing convex program package probably should give you close to global optimal solution. I'm sorry? Well, it's equivalent. That's the point of a geometric program. It's something like original problem is not convex program. However, by just doing some change variable, some transform, you convert the problem into an equivalent convex optimization problem. I think one analogy that I think in the first class, I have an example where you have like a nonlinear program. By just introduce some new decision variables and constraints, you make it a linear program. No, of course, only like this type of problem, geometric program can be converted into convex program. Oh, no, that's not right. I mean, we already see this can be converted. There are some other problems where original optimization is not a convex program, but after some careful design, you can convert the problem into a convex program and solve the optimal solution and then get back to the original problem without losing anything. And that's the beauty of studying like some structure of the problem, rather than just using very generic routine to solve that. And of course, the authors studied this problem, and they made a round-off on this number of shifts just to 16. I don't know why they don't choose 15, because to me it's more obvious that you it's, well, I'm sorry? Yeah, I think so. They want to at least, in order to maintain shift operation, say you cannot be too, you have to be conservative. You cannot be opportunistic. And okay, so that's like one example where you see geometric programming being applied to some engineering optimization problem. Here's another one. And this problem, you can say it's related to some chemical process. Anyone know what this is? And even by looking at this flow diagram, can you make sense out of this? Like the reaction and fractionator for the hydrocarbon product. Like intuitively, what does this do? I'm sorry? Control some chemical reaction, right? And other than that, I just wonder if anyone knows any particular way to describe about, for instance, the fresh acid to the spent acid through the chemical reaction, what kind of like hydrocarbon product should be like should be processed either to get this acrylic product or recycle to some isobutane recycle part in order to do the chemical reaction again. Yeah, yeah.
That's, I think, the input. And out of all of this, you get something that's...
Yeah, you have the product. Of course, you have some feedback in the chemical reaction.
Is the real input. The rest of it is something that helps the reaction.
Yeah, and then you have this, product, and that's like some chemical reaction process.
I have no idea what both things are. I've never heard that word before.
I don't know, because these are things related to the chemical for this process. And that's basically how they study the compound of this. And then this olefin feed, they count like the lower bound and upper bound for the barrels per day. And then also they have this isobutane recycle and the acid addition rate, so on and so forth. And what? And basically that's somewhere you find optimization problem. And I think in bioinformatics, you probably don't study very hard to get into such a level of detail to really see the chemical reaction of the protein or whatever. Okay, so most people don't really see engineering problem as detailed as studying this. But then, for instance, you have these compounds, and then you need to study the product of this. And we have to express the regressing relationship in the form of some constraints, which in general specify some relationships between the between the input and output in the reactor and the fractionator. And these are things we need to study. And how do you study? Well, I don't know, because I think some chemical engineers, usually they either put this into some perspective of the like a physics-based understanding how the chemical reaction happens. But in general, that's too tedious to see the macroscopic picture of what's going on. And another way is just say, well, we monitor this chemical reaction plant and then collect data and then try to fit some curve and use nonlinear regression to get, you have some empirical model, like x4 should be some function of x1 and x8 with this, but then you fit those values based on your data. After doing some nonlinear regression, they found that decision variables may be related by these 4 different regression equations, meaning that, for instance, the variable x10 can be expressed like a fan function of x7, so on and so forth. And also, with these constraints, you can, in effect, simplify the regression problem into some newly written constraints because of the regression, because of this relationship on the decision variable from this. And by reformulating the constraints in such a form, what do you see? They are polynomial. These are all polynomial constraints. Okay, and what's the difference? In general, for instance, for linear program, you can see all the constraints have to be what? Linear combination of your decision variables. And now you see polynomial function as what? Some extension of this kind of linear constraints, right? Yeah, of course, it's more generalized. And also, it's still tractable because it can be converted into a convex program. Okay, so that's something very nice. And then, of course, there are some other constraints on the mass balance. And that's also very hard to express as a chemical reaction. And in general, it can be bounded by some upper-lower value for those decision variable. And also need to build what? Some kind of regression model on the mass balance equations. And these could be obtained through some study. For instance, for volumetric reactor balance and acid mass balance and this so-called isobutane recycle balance, they all can be studied by some nonlinear function where you find those coefficients by some field test. And sometimes you'll say, well, it's hard to determine this simultaneously. Then you introduce ancillary decision variables, and these are to be eliminated later. Why you need this? Because what? I think I would say some people like polynomial functions. If you cannot write the constraint in polynomial form, then what? You always think about how to transform that into polynomial form. And that's after reformulating the constraints with some additional auxiliary decision variable, it looks like the balance constraints are of this form, where you can see that each term is what? Monomial function. So the collection of those terms are polynomial. And that's the constraints we have. OK, so what's next? Well, now that's the key, right? How to calculate the profit. And of course, need to study the cost for instance, for different like olefin feed cost and this alkylate product value and so on and so forth. And in general, the total profit per day to be maximized contains different terms, something like you have the yield and then the product of this, and then subtract out all the materials you put into the chemical production. So the nice thing about this objective function, you can immediately appreciate that what? Polynomial function, OK. So with these examples, I hope that you see what? It's a generic formulation that can be applied to different optimization problems. If you have something to comment. Optimization problem. Well, I'm not saying convert any nonlinear optimization, but I would say convert something that looks like polynomial function. Yeah. Yeah. Like a polynomial. Yeah. Yeah. Yeah, well, polynomial actually has some specific restrictions. For instance, you can say it can be only a linear combination of what? Monomial functions. A monomial function is only what? The product of your decision variable raised to the certain power. Yeah. Yes. Yeah. Than some difficult and in general nonlinear functions. Because this type of problem, even though at the very beginning looks hard to solve, but after converting to convex program, then it's tractable. It's similar to a lot of optimization problems formulated as a linear program. If you think about most of the computing power dedicated to optimization, I would say at some point over 90% are solving linear programming. Is that surprising? I would say so, right? For instance, if you think about the computational effort made in computer program, solving all the optimization, like operations research problem, over 90% actually are dedicated to just solving linear programming. In real world, can we see so many abundant linear programs? No. In general, only people who study the field and make engineering approximations can change the optimization problem to something which can be attacked by linear program. And also, most of the linear program can easily handle like tens of thousands of decision variables. While in other optimization contexts, you never know what's going to happen. Okay, so to make the profit function fit geometric programming, you need to also make some effort, minimize the negative profit instead of maximizing the profit. And also you need to eliminate somehow x5 and x2, which could be taken care of if you put some constraints. And this, for instance, if you want it to be always a positive function, then of course another way to make sure that the minimal value is positive for the profit, you can make adjustment on the objective function by putting some large value. Well, 3,000 may not be large enough, but maybe for this problem, the authors studied that, saying that's good enough to make it run. And then what? After so many tedious manipulations on this, the objective function, the regression and mass balance constraints, as well as upper and lower bounds on the decision variables for this chemical reaction process optimization problem is finally formulated as what? A geometric program. Okay, so I guess this lecture is mainly just to give you some exposure to some applications where taking the advantage of some structure of the optimization is important, especially when you have problem that's non-convex. If you can make it convex, usually it makes life easier. Any questions? Okay, so maybe let's take a short break. After that, I guess I don't have a lot to present for tonight, but I may want to hear some input from each of you about the progress of your project, or maybe some other aspects that you want to say at this point, like what things you would like to know and what things you probably want to know. You don't want to know. Probably you'll say, well, maybe next time, maybe Libby wants to take over and talk a little bit about her project or things. I don't want to always teach optimization in terms of the tedious details, but I want to give you some idea about like what can be done when you can properly formulate the optimization problem. Okay, so maybe let's take a short break first. Sure. Oh, homework. Thanks. Oh, what does this mean by argument? Well, for instance, if you want to find this whole function as your decision variable is x, right? An argument maximum means when this function is maximum, what value makes it maximum? And that's you x star. X star, for instance, for each I, you have this utility function as a decision variable I. So that's xi, right? This is for the S decision variable. That's the utility, and this is the multiplier for that.
Okay.
Okay, so argument maximum means basically you find the decision variable that can achieve the maximum. If you just say maximum, that's just the maximum value of your objective function. Okay? No problem. Yes.
In our form formulation, why do you want to solve this maximization problem of sparsity?
Uh,
Why you want to maximize the sparsity for A?
why should I maximize sparsity?
Yes, we think if we minimize.
Oh, sorry. I think this is ridiculous. It should be
It should be just minimize.
minimize the L0 norm. Yeah.
Yeah, so this
Yeah.
is the
Yeah.
confusion.
Thanks. Yeah. It's Yeah. It's like maximize the sparsity means minimizing the L1 norm. Yeah.
Do we need to use lasso or we can use other?
Well, there are different methods. I would say, yeah, lasso is quite effective. Yeah. Yeah, for regularized least squares problem, lasso is very effective. Yeah, in general, I would say CVX, I mean convex program package, would be good enough to solve this. Solve any kind of even second comb program and some other extension of this.
So we can make use of some existing algorithms to solve
Yeah.
deal with this intermediate step.
Yeah, of course. I mean, the whole thing, you don't need to design your own algorithm. It's like if this is standard, you want to take the advantage of the standard optimization package, especially when you deal with large-scale problem. Usually that takes time to test, like when you have like thousands of decision variables.
Actually, in this problem, we are trying to use, we are not planning to use large-scale data because,
Okay.
Because one of the algorithms is, as I have written, right,
Yeah.
we are also going to we want to reduce and check exhaustively every time that we want to also reduce some of the basis elements which we have already added.
Okay.
So that is a kind of exhaustive search, so it might take a lot of computation of this. So
Well,
for this algorithm, for now, we don't want to assume large.
yeah, what I'm saying is, in general, depending on how large you consider large, I would say if you consider like a nonlinear optimization with 5 to 6 decision variables, it's already large because you don't know what will happen. But for convex program, you don't care too much. Like in my term project posted on Blackboard, at least you can handle maybe over 60,000 decision variables.
60,000.
Yeah.
5,000. So 56 squared.
Yeah. Yeah, you can handle maybe that size. Yeah.
I'm not handling.
Yeah. Well, that's close to realistic optimization problem. It's just like two. Yes. Each pixel, yeah, you need to reconstruct the pixel value. Yeah. Why is it's tractable?
Why would you make it that?
Yeah. Like a linear program takes maybe a few seconds to finish this scale of problem. Well, convex program is not that harder if you properly scale like how to optimize the convex program. Yeah, you can try. Yeah, that's interesting. Yeah, FPCAM is not that bad. It has it has a lot of options to choose to explore. However, in general, you cannot rely too much on FMinCon. Even in the new computer assignment, you can try. Well, first, for instance, for some objective function, depending on what your initial guess is, it will easily get into a local optimal. And second, I would say of course, that's problem dependent. Second is like if you know how to choose a proper option, that means you already know basically all the pros and cons of those state-of-the-art optimization algorithms. Otherwise, if you say just leave it the default option, that may not be good. I would say upon completion of this course, I don't think you need to do extensive MATLAB programming, but you do need to have good knowledge about the state of the art of the optimization field. so that later maybe when you have some problem, you know where to look for some additional information. There seems to be some truncation in the full screen, I just realized.
Oh, it's because do you remember when before we could get to slide 16?
Yeah, we cannot, well,
Zoomed in right now.
okay. Oh, I see, so, yeah, so maybe here, if I can, how should I do that? Okay. That's okay. Okay. Okay.
Yeah, it's chromatic. There you go.
Yeah, that's better. Okay, thanks.
Yeah, the blue is off. Anywhere that you see black, look to the right by a little bit. You'll see the same thing.
Here?
Chromatic aberration.
Chromatic.
Because when you're taking a picture, like,
yeah.
You have a lens that disperses the different colors separately. You'll get this effect on the photograph, depending on your lens.
Well, so you expect more examples, I guess.
Right. Chromatic is
try to make life easier so that we can. Well, because last time, I think Mr. Gang Liu volunteered to take recitation notes for something very challenging, and today he couldn't make it. Maybe that overwhelmed him, even though he said, why should I take the trophy, and then couldn't keep the promise. No, I didn't prepare any trophy for tonight. Sorry. Well, that's not a chemical reaction, I hope. I do have some allergy, probably. I mean, I just feel my throat is a little bit sore. Yeah, I think it's allergy season, but this is not contagious, I promise. All right, so maybe just let me try to highlight this important aspect of the geometric program. You see, the next thing is that originally we know like linear program is easy to solve. You can scale to large scale optimization problem running standard linear program package. And now we say, well, convex program usually is relatively easy to handle. Well, may not be, but still you can pursue for global optimal, right? And if you choose the right way to do the gradient descent or whatever. And some problems, some nonlinear optimization problems can be converted into convex program. And geometric programming is one particular application where it draws a lot of attention in many engineering problems, which actually can be solved efficiently. And examples from various engineering areas have been studied in the field of operation research, which people try to see how to apply geometric programming or even to approximate the original optimization problem by geometric programming, and then try to solve the problem using efficient algorithm. Once you get to a reasonable solution, of course, if you still want to do general nonlinear optimization, then at least what? You have a good initial guess. And with that, you probably have better chance to get to global optimal. In particular, you can say there are some problems where geometric programming are very useful, like in chemical engineering example, and also in the shape operation optimization example, where you'll see some like maximizing the profit or reducing the operating cost has some nice structure with respect to the decision variables, which can be easily written as like a polynomial function. And sometimes people try to extend this idea to so-called signomial problem, where it's not exactly geometric programming, but still you can have a good way to convert that into geometric program. I think I presented some examples to show you some extensions where original problem is not a geometric program. You can convert that first to the geometric program by introducing additional decision variables and constraints. And after that, you convert the problem into convex program. And there's one interesting application where I just mentioned, but probably needs a lot of space to present that, and you guys will get bored. For instance, now as an engineer, of course, you want to maybe study a little bit about the more complex network. For instance, internet is considered very complex, right? And the protocol, I think some of you probably know, to maintain this data packet transmission is called what? TCP/IP. What does that mean? Okay. And okay, and that means what? You regulate how the packet should be transmitted, right? And do you know like the underlying principle of this TCP/IP? Like, yeah, but roughly how does it work?
Basically, it sends the packet, and it basically will begin an acknowledgement back that the packet will receive what it was sent.
Okay.
And then if it doesn't get the acknowledgement within like timeout,
okay.
It does something along the lines of.
So you need to.
It'll try to like resend it as well.
Okay. Okay.
It'll try to reroute it.
Okay. So it's like what? You can say it's like some kind of a distributed protocol or algorithm that, for instance, each student can try to transmit some packet, right? And then what? And then wait for the receiver to acknowledge, right? If you don't see that, then what? You think there might be some congestion during this transmission, right? Then what do you do? Send it again? And you keep doing that? I think that's a good idea, of course, but then.
I think it like backs off by a factor two.
Okay, so you reduce your transmission rate of the data packet, okay? And sometimes if you say, I get acknowledgement, and then what? Maybe I increase my transmission linearly, and you back up what? Exponentially. Why is that? Well, intuitively you can say, well, if everyone try to flow through the network, they will compete, and there will be potential congestion, right? So you don't want, so you go linearly. That's like you try to be a little bit what? Not too greedy in the packet transmission. But whenever you don't receive anything, that's like some indication of the network congestion. Intuitively, what do? You back up. But why you back up so fast? Because during the congestion, no one can really transmit anything, right? For instance, if one router needs to send the packet back and forth, then everyone experiences essential delay because of that. Then I need to back up fast, and you also need to back up fast. But should we always back up exponentially fast? That's one reasonable question to ask, right? Originally, we don't know. And also another relevant question is, for instance, can we have better protocol, scale better with respect to future networking technology, like fast router, fiber optic, right? Maybe, yes. Okay, so you heard about that?
Well, I know TCP is far from ideal. The reason why it's still stuck is because it's used everywhere.
Well,
the effort to take to sort of replace it is not worth it.
Are you talking about like some flow-based, like routing algorithms?
Well, it's not about routing. It's just the basic like protocol for data transmission, like similar to TCP/IP. Of course, you have the like maybe IPv6, like also higher stack protocol. For instance, along TCP, you have different flow control mechanism built in. You can say change that to so-called fast TCP for fiber optic. I'm talking about, for instance, in principle, what are the assumptions you make? Like you assume each individual user needs to obey that, right? If I'm greedy, for instance, you use TCP, I try to increase exponentially, I can gain. But if everyone does that, it will be a disaster. Then, for instance, can you enforce the user who has this self-interest to manipulate not to do that?
I think there's some ATM algorithm. I forgot what it's named, but it's like a virtual service.
ATM, you mean asynchronous transfer mode. That's for, is that ATM? Oh, the ATM machine that I can get.
I think it's basically sort of like you set, via the router, it's like you set up a virtual link between a computer, between the two links.
Okay, yeah, I know that ATM, as it stands for asynchronous transfer mode, is just one, like a hidden layer I think somewhere in between, like physical layer, like you use SONET or some other things, fiber optic, to the higher level, how to handle those like packet switching network, right? The fast packet switching network. And TCP is usually upper. TCP/IP can be implemented over ATM. That's what I'm trying to say. Okay, well, I'm not expert in computer networks, but I think this is what I learned in my undergraduate years, which now I think probably is still true. And the point I want to mention, like this TCP protocol is this like transmission control protocol, is that originally, like what Sai just said, people think that for this kind of distributed protocol, it may not really scale very well. For instance, now we have huge complex network. You say, well, because this is the protocol we already adopted, there's no way no incentive people can improve upon that. I feel that's not true, right? If you can write a better protocol than TCP, why don't we adopt that? If that can save bandwidth, if it can improve the efficiency of the data transmission. Of course, there's always an engineering trade-off. Not until, I think, in the 1980s, there's an economist actually studied this problem. I think it's Frank P. Kelly, who actually presented a nice idea saying that if you look at any overall network utility as opposed to just individual utility, of course you can say any distributed protocol, if you can cast that into optimizing a global network utility function by by implementing some distributed protocol, then the whole design can be cast as a network optimization problem, where you have a global objective function that can be decomposed into individual objectives, so that any protocol design could be cast as making optimizations with respect to a network utility function. And based on that, in fact, later people show that by geometric programming and some nice conversion, TCP/IP, this TCP protocol, this so-called flow control by like linearly increasing the transmission rate and exponentially back up during congestion, is actually not a bad idea, because it approximately optimizes some concave network utility. And what's the purpose of talking about this? Well, I would say geometric programming provides a nice view to build a connection for seemingly very difficult engineering optimization problem. Now, I think some people studying in this protocol design probably are very familiar with this kind of network optimization, network decomposition as protocol by putting protocol design as an optimization problem rather than a pure intuition-based networking design principle. So that at least shows optimization can be applied to diverse areas and very challenging problems. Okay, so I guess that's what I want to talk about, the geometric programming. And now I hope that to get some feedback from each of you about like the course material, project, or maybe some upcoming assignment, what you feel about this course, and what you've done, what you expect to see, what you want to know for the next lecture. That's probably what I need to talk about. And then the podium will be yours for the project presentation. Yes, Bryce.
No problem, man. I don't have a clue of what you want for the third project. I don't have a clue.
Do you want to choose the term project assigned on Blackboard?
I mean, I can, but still, even if I chose that, I probably feel more comfortable doing this project.
Well, I hope to get some specific suggestions on, for instance, which part you're having difficulty, and some part if it's specifically that I cannot address now, but I hope that maybe we arrange some office hour to discuss about that afterwards. But I do hope that you provide me some specific suggestions on which part needs to be explained better.
I mean, for example, when you talk about optimization, a communication system where you have different channels of communication, and you try to find the best that will allow you to send your data from the transmitter to the receiver fluidly.
Well, I don't think I covered that, but go ahead.
That's where I'm figuring out the truth, because I don't know which part of the course really talk about this specific problem.
Well, sometimes.
You want me to define the problem of my project.
Okay, so yeah, so for your case, I don't have much background about the communication problem you have in mind. And also sometimes it may not be an optimization problem, that's for sure. For instance, sometimes it can be like some design problem where you need to understand about the communication the communication channel or model, or maybe coding problem, how to encode the message you want to transmit, and those may not be optimization problem. However, for instance, you'll say, I want to do like a maximum likelihood decoding, finding the most likely sequence among all the possible messages that I could receive from the transmitter. Then that's optimization. Then, of course, you can explore like what algorithm you want to use. But in general, that's mainly discrete type of optimization. And also, if you have a better way, I would suggest that for those of you who have not sent me, who has not sent me the description of your project, you'd better, for instance, write 1 or 2 pages, describe about the problem and the method you want to use to attack the problem and what you expect after applying some optimization technique, so that we can have some discussions individually. Yes, Sam.
Well, what happened with me, I mean, when I emailed you, is I was working on a method and then the results were bad. So I'm worried that I'm going to work on something, and come term project presentation time, the results aren't good at all.
Well, I would say sometimes I need to know more details in order to judge. For instance, a method doesn't work, still it's something we can learn, right? Because sometimes, for instance, you'll say, well, before this TCP protocol, maybe people tried some other method. For instance, you'll say, well, if there's a congestion, we don't back up, just let the user to decide what to do. And there's also another protocol called Aloha for multiple access. Something like in wireless communication, you can say, if I'm talking, other students cannot talk, right? So if we all talk simultaneously, nobody can listen. So we have to take turns. Let's assume that we all blindfolded, and then how can we do that? We have to have some protocol. I say, now let me speak first, and then I speak, and then say, now I'm done. Okay, so whoever wants to say, please announce yourself and speak, right? And then, for instance, in wireless communication, how can you make that happen? How do you choose the protocol? If multiple users want to access the same channel, want to use the same open air to communicate. And in network, if you have some kind of, maybe, how should I say, some kind of shared media like Ethernet, how are you going to design a protocol that everyone can share this media but avoiding potential collision? There are different ideas, yes?
Well, depends on the algorithm. Some have collision
detection, yeah.
Whereas others try to.
Yeah, like Aloha is something that doesn't really rely on collision detection. It's just, if there's a collision, everyone randomly back up a little bit. And then hopefully that will resolve the collision. Because of the randomness of the backup time, that will, even though that's simple, right? But how random would that be? What distribution you want to put? For instance, if you say I put a uniform distribution, it doesn't work, and then you study why it doesn't work. Still, when you say I try to optimize this distribution, and still it doesn't work, and that we can still gain something. That's why when you said that you have some of your own research problem, you applied some optimization technique that doesn't work, I need to know more information in order to determine if I would encourage you to pursue on that for term project or not. Well, any other student wants to talk a little bit about? No, not at all. I'm sorry? Okay, and what do you expect for, I think we have, how many lecture period for this semester? 3 or 3, right? I think last week will be the oral presentation, I assume. And then prior to that, I think I may spend some time just to summarize. And also, I think some of you may be very keen to know the final exam, like what to review, to prepare, right? And then maybe I should say a few words on that. What do you expect? You want to have a closed book?
Yeah.
You want to have a closed book
Yeah,
exam?
open books are usually very difficult.
I'm hoping for a take-home open book.
Yeah.
But then what's the difference between that and term project? I mean, if you have take-home open book exam, usually it's hard to really monitor the, I mean, usually I'm personally not against that suggestion. The only difference is that usually the university has some regulation. If they see final take-home exam, they will not call that a final exam.
But can you not have an exam?
I would hope that the final exam as a chance for you to sharpen your like mathematical skill in doing. Well, sharpen a little bit on the mathematical skill, meaning that, for instance, solving some small problem or understand a little better about optimization in conditions. I'm sorry? Well, I would say some homework problems are harder than the exam questions because it takes time to. Yeah. You mean all of them?
All of them should be harder.
It also takes time, right, for homework assignment. Yes.
Well, I don't know anything about everybody's availability plan,
Okay.
but I really think that with the homework, with the final exam, just is homework is it's going to be really tough. The reason why I'm saying it is the last homework is about chapter 21, and in order for like reading the cover yet. So I'm saying if you do final exam like this, I mean, totally for me, it's really gonna be tough.
Oh, I see. Yeah, yeah, I heard your message. And the reason that I try to explain to you about the difference between, like, for instance, graduate level course and also sometimes the course material versus like the real need that you would expect from a course is that sometimes you may say, well, one goal is, of course, get an A out of any graduate course you take. And another goal is, for instance, hope this course really will be useful for your future research or engineering career. And I think the last thing is about, for instance, how that enforce you to develop your own learning habit so that later, without having an instructor teaching you, okay, read this part, prepare this question, so that will be useful for the exam, you'll have your own way to learn new things that you don't know very well. For instance, like read chapter by chapter until chapter 21 or 22. And with these three objectives, I would say, of course, you need to have a well-formulated optimization problem, right? Because, for instance, if you only focus on objective number one, then, of course, you put emphasis on, like, I want to get at least 10 out of 10 or 11 out of 10 on every single homework assignment. I want to make sure that I cover every single, I want to get every single point covered in my notes and then try to prepare very hard, just prepare for the exam. And sometimes I feel, well, that's not really the best way for each of you to learn new stuff. And sometimes you don't have to be perfect on every single homework assignment, though. But you got to try to make sure that you put serious effort into the learning process. So that's why I need some serious feedback. Like, for instance, if you have difficulty learning some material, maybe that's very hard for you, then at least find a way to approach maybe to other students or to the instructor, so that I hope that I will try my best to help you pinpoint to where to look at, which reference to read, or try to explain to you about the basic concept repeatedly, so that I hope that will be helpful.
You should do some amount of explanation, because I could also pick up the textbook,
Yeah.
registered in the class,
Yes.
and read up to chapter 21 and
Yeah.
solve that problem.
Yeah.
But I'm taking the class because I want some instruction.
Yeah.
So, I mean, it's nice that you're trying to force us to learn on our own, but also
Yeah.
we're here because we want to be taught something.
Very,
So
yeah,
there's a balance.
yeah. So yeah, that's why I'm trying to repeatedly trying to get some feedback, especially, for instance, if I need to explain a little bit more on certain chapter of the textbook, that's useful. And not just this textbook, but also relevant references that I put on UNO Library Reserve Desk, which I looked into that, and it seems that nobody checked out any book yet.
That's to be expected, I think.
That's to be expected? Well, usually no. I would say when I was at Connecticut, I think most of the unreserved book usually has been checked out very frequently by the students taking the course. Well, I mean, doesn't mean they really read, but at least they skim through to look at what the instructor wants to explore. I was a student, yeah. So, but doesn't mean I keep doing that. I'm saying that all students taking the course usually want to know about, like, supplementary reading, other things, at least to know, like, where to go further. For instance, after taking this course, maybe you only memorize some basics, but still you have better idea what's going on with advanced optimization technique and maybe some interesting engineering optimization problem. Then you know where to read the reference. And of course, you also need to know how to really understand some advanced stuff gradually, I hope.
Yeah, but I think, like, if there were an optimization tool,
Okay.
then certainly whatever references you assign, people
Yeah.
should be investigating. But for like an introductory class, it's nice that we're getting.
Well, and also we don't have optimization 2 or 3 or whatever.
I know, but
Yeah.
you can't just lump all three into one class.
Yeah.
I mean, because I can't learn that way, you know.
Yeah.
I'm taught step by step.
I see. Yeah, that's true. So
Scope problems.
yeah, I think so. And fortunately, we also have the luxury to use this media room. so that at least if you do want to go over some part of the material, you can recap a little bit. I mean, just later, for instance, for you to look into some point of interest that might be useful for your research. Yeah, other than that, I would say, well, it's also my first time covering this course, and it has a lot of my research flavor in it. So some part could be tough, and some part I don't have time to explain rigorously in math. And some part I probably, because I have limited knowledge, I cannot know the details of the engineering need for some particular optimization problem. But hopefully, as a whole, I would say I want to have maybe larger picture for all of you to look at the engineering optimization, because I think most of you from diverse areas with specific interest, and try to find something useful for your own research, for your own experience. So that's why it's hard to make a good balance. And at this stage, I would say I would still hope that if some of you would like me to maybe make some specific comments related to, for instance, if you pose some questions for me to think about, then I can respond. Like what Rustin suggested, is it possible to maybe highlight some basic stuff in each chapter, like what are the important things from my perspective? I will try. But I need to have some specific input in order to respond accordingly. And of course, I hate to ask, but do you guys feel that you really learned anything from this? Or it's hard to say. Through. Okay. Yeah, and read, and also maybe look at some MATLAB example, maybe write something on your own. And that, well, that I would say that's expected. I mean, for most graduate level courses, I would say that's probably the way you can learn, and you probably later will learn faster. I think maybe for some other maybe introductory graduate level course, maybe not computer assignment is not that demanding, but for optimization, unfortunately, it is indispensable too.
I like mixed feelings about this.
Okay.
There are certain things that I've actually really been interested in, and I would go and learn on my own, write my own code. Right?
Okay.
So if I have a problem in mind that I want to solve,
yeah,
I can very easily like spend the time to learn it.
Okay, cool.
But like some of these homework assignments, they've been on things that I would like to know, but they're not something that I would spend my time doing for fun. You know? So it's kind of hard, but I have to spend my time on it, even though it's
well, I think the first time I mentioned about like the so-called coloring this balls with minimal discrepancy. I think there's one joke, like life is full of discrepancy. Why don't you want to make it smaller? But to address your question, of course, I think everyone has an opinion on certain course. I don't expect everyone can like this optimization course. I think the problem is usually from retrospective, how well you can actually reproduce the learning process later without relying too much on the instructor. That's something I know it's hard, but that's what a graduate course has to push very hard to pursue on that aspect. And with that in mind, of course, I also need to have some good interactions with all of you so that at least you understand me better on what I expect and what my thinking process is. And sometimes it may not be the best way for you to comprehend. And sometimes I also need to have some constructive criticism so that I can improve. Later, if there's a chance I teach this optimization course again, other graduate students who take the course may benefit. So Gordon, you want to say anything? No. And what about Mr. Wu?
One question about our presentation. So we have our presentation
Last week,
before the final
before the final exam.
So 3 hours for all of that.
Oh,
2 hours for all.
well, I would say as long as it takes to finish. But usually each presentation takes about 15 minutes, and then allow 5 minutes for questions.
20 minutes.
Yeah.
So we have
But there would be some transition, I would say, and because usually I would say there might be some delay due to presentations. Yeah. About 3 hours. So that's why I'm asking the opinion. For instance, if anyone volunteers to do the oral presentation, yeah. Yeah, a little bit earlier, so that if you, and also you can say take the luxury that you get early feedback about things you've done.
How can I have a bonus function for those that present?
Oh, bonus function. Okay, that's a good suggestion. Yes, I think seriously, I think so. Maybe, for instance, like a 20% bonus toward the oral presentation grade for those for those presented early, for instance, and the oral presentation. I hope that everyone can help me at least do some serious evaluation on the oral presentation. Because when I organize a graduate seminar in the past few years, I usually collect some kind of student peer evaluation on the oral presentation. I also even type in some constructive comments on Blackboard so that when you see some suggestions from you classmates without knowing who said some harsh words. Usually they don't. They just put it in a very nice manner so that you actually learn a lot from those perspectives. And sometimes maybe if you try to be constructive to make suggestions to other people, you also get some well rewarded because usually I think you guys know, right? So I will rely on you to put some weights on like the peer evaluation of the oral presentation, not 100%, but significant amount of weights. And also like what Sarah suggested, I think it's a good idea that if we do have volunteers to present 1 week before the final week, then we don't have extended long hours to complete all the presentations. That means 2 weeks from tonight, yes. That would be possible for some of you who already made some initial progress and want to listen to some comments. I'm sorry?
The transition and distribution conference.
Oh, really? I don't know, but you have a presentation for that? Or?
No, but I want to attend the conference.
Oh, I see.
Yeah. It's not at night, but it's going to be always.
Okay.
I don't know.
Yeah, I heard about that conference. Also, I think there are some other conferences that might be close to the end of April. So but still we need to make some balance because this is also a university course. I cannot be too lenient on that.
It just means that I'm not getting bonus.
Okay. So I guess next time I will try to cover a little bit on maybe semi-definite programming. You guys heard about that or not at all?
We read that chapter.
Okay.
21.
Well, but the actual problem you solve is about duality, in fact.
Yes,
and
but
that
itself has some definite programming.
Yeah, because it's some extension of convex program.
Right.
Like a geometric program is one extension, semi-definite program is another. These are popular ones. After that, I think I've done all the optimization that probably you should know, at least you should hear the name and feel familiar with.
Yeah, I feel like you never actually learned the simplex
Simplex, no, I didn't cover.
Right, but I feel like everybody that I've said, hey, I'm taking optimization, they're like, oh, so you know the simplex algorithm.
Okay,
No,
and
I've never seen it in fact.
and simplex is actually relatively easy to understand if you, yeah.
That would make a good, here's an algorithm, look,
Yeah.
it works.
Originally, I thought I want to cover a little bit on interior point algorithm, but then I think the level of difficulty is something like if it's just introduction level, then you hear about it. So okay, so it's from the inside, feasible side, and get to the optimal. That's it. But then if you want to get into a certain level of mathematical rigorous, it takes longer time. So I think same thing for simplex. The idea is simple. And then the actual details, for instance, pivoting and other things, and the original simplex can be modified. And also the technique is considered obsolete somehow. It's still still a classic thing to know. But other than that, I would say the actual technique was obsolete. It's considered obsolete because most off-the-shelf routine usually based on so-called primal deal interior point method. And that's why, of course, simplex in itself can also be applied to like global optimization. But even that, for instance, even though you like F-mean search a lot, right, with that option. Yeah, but still, I would say for serious large-scale problem, that wouldn't work. Even as good as simulated annealing, it's hard to say, but different people have different opinions for sure. Okay, so if you have some suggestions, then of course I can maybe adjust a little bit. Otherwise, I would say maybe next time I will try to prepare just a little bit introduction on semi-definite program. No, you don't like it. Okay. Okay, so well, you can propose something that you're interested in. Sometimes unfortunately I cannot really cover, then at least I can.
I feel like if you spend maybe half an hour
On simplex.
Half an hour on
interior point.
Half an hour on a couple other things that you can't dive into in half an hour.
Okay.
But I think these are useful algorithms. They're famous.
Okay. Yeah, that's fine. I will try. For instance, just you guys are interested in knowing simplex. What I'm saying is probably my cover for half an hour is nothing but what you can read from the text about simplex. For instance, if you want me to try now, I can spend 5 minutes on simplex. Not now, okay, that's fine. Yeah, but okay, so yeah, of course, simplex and interior point are really something very useful, but depending on the depths of what you want to know.
Well, like if I were interested in simplex, I could also go on the Wikipedia page and read about simplex.
Okay.
Right?
Yes.
But if you present simplex,
I wouldn't be better than Wikipedia most of the time. I might be worse.
well, never mind.
Well, it's okay. But seriously, I would say Wikipedia is not really like official publishing on things you want to learn. But still, I think it's well maintained, well documented. I would say, well, it's like some resource you can learn where to look at good references most of the time, right? And I would say, for instance, conventional teaching, like classroom teaching, usually eventually might be replaced with the help of Wikipedia or maybe iPad or whatever. And then, you doubt it? Well, conventional teaching could be changed, tailored toward, for instance, when you learn simplex, you spend some time dive into the background, and then the class could be restructured with more interactions among different individual students to address individual needs.
One of the nice things of having a teacher is that the teacher can see what problem a student is having.
Yeah, but sometimes
instill clarity.
Well, sometimes I would say among 100 rated, like excellent rated teachers, maybe only less than 10% can actually do what you said. Yeah, well, in fact, because teaching is usually, especially at the graduate level course, it's a mutual interaction. That's what I feel. Because without some feedback, it's hard. It's just like I prepare to sharpen my mind in order to do the best from my part. On the other hand, I would say students, if they are eager to learn, sometimes they're unsatisfied. If they're not eager to learn, then they're also unsatisfied because from other aspects. But on the other hand, I would say, yes, it's definitely helpful to look into Wikipedia. But of course, I think another way you can organize a little bit better about the course material would be just also spend some time on course Blackboard and also maybe skim through some supplementary readings, at least have that in mind. Later when you have research problem encountered, you have some references that I personally feel useful. And okay, so with that in mind, I guess I will try to prepare something. Well, I will try to prepare something maybe related to simplex or interior point. And also, some of you may also want to hear a little bit about semi-definite programming, so I will try to see what I can do next time. And that will be my last show, and then it's all yours. But bear in mind, if you do encounter difficulty in doing homework assignment or term project, please try to have some interaction with me so that I want to know some specifics about the difficulty you have so that if I may, I can post some feedback. Either we can discuss in email, but I would prefer if you use discussion forum and post your question there, then maybe even other students can participate. Okay, and thank you very much. I think we ended early for tonight because some of you may lack that very much, which is rare in my class. Okay, thank you very much.